Welcome to the 47th lecture of the open course on diffusion in multi-component solids. In this lecture, I will discuss intrinsic diffusion, that is, diffusion studied with respect to the lattice fixed frame of reference, or in other words, Kirkendall frame. I shall first explain the Kirkendall effect and later describe how the net vacancy flow gives rise to shift of marker plane. We will also go over the derivation of Darken's equation that relates the binary interdiffusion coefficient to the intrinsic diffusion coefficients of the two components. Today we will talk about intrinsic diffusion. So when we studied the diffusion under thermodynamic driving forces or under the chemical potential gradients, we wrote the equation Ja equal to minus La dou mu A by dou x. Remember, this applies when there is a vacancy equilibrium achieved at every plane within the diffusion zone. In terms of mobility, we can write it as minus MACA dou mu A by dou x, where MA is the mobility of A and CA is the concentration of A. And in terms of intrinsic diffusion, we wrote minus dA dou CA by dou x, and we derived the relation dA is equal to MA RT phi, where phi is the thermodynamic factor, which is nothing but 1 plus d ln gamma A over d ln x A. Gamma A here is the thermodynamic activity coefficient. Now this flux is actually the intrinsic flux, and so dA here is basically the intrinsic diffusion coefficient of A. When I say intrinsic diffusion, it is the diffusion under purely thermodynamic driving forces. That means we are not considering any movement that might occur in the lattice planes. So to illustrate this, consider diffusion between two different alloys, and suppose A diffuses from left to right and B diffuses from right to left, and suppose the intrinsic diffusivity of A is greater than that of B. So obviously in a given interval of time there will be more number of A atoms moving from left to right compared to the number of B atoms moving from right to left. Because of this, there will be a net mass transfer across this initial contact plane. Hence, it will look like the left portion of the alloy has shrunk, whereas the right portion of the alloy has expanded. Now if we can track the lattice plane which was originally at this initial contact plane here by some kind of markers, the markers I am showing with these circles here, such that the markers stick to that lattice plane and move with the lattice plane if the lattice plane moves. Now after diffusion, since this part has shrunk, the left side has shrunk and the right side has expanded, so if we obtain the initial contact plane by the metano analysis, it will look like these marker planes would have shifted to left, and this is called the marker movement or Kirkendall effect, because Smigelskas and Kirkendall were the first one who reported this kind of movement. Now, if we measure the diffusion flux with respect to a frame of reference which is fixed to the metanoplane, that is the plane which we found as initial contact plane, the flux would be different than if we measure the flux with respect to the frame of reference which is stuck to this marker plane, and the diffusion flux with respect to this frame of reference stuck to the lattice plane or the marker plane is referred to as the intrinsic flux, because it will give only the Fickian term, whereas if we measure with respect to the metanoplane, there will be a term also because of the drift that has caused because of this lattice movement. So, in other words, if we write the equation for interdiffusion flux Ja tilde, it would be the flux, the intrinsic flux, that is with respect to the lattice fixed frame, which is denoted as Ja plus concentration time Vk, where Vk is the velocity of the marker plane. This new frame of reference, that is the lattice fixed frame of reference, is also referred to as Kirkendall frame, and so we write the notation for velocity as V subscript k. Why this movement occurs? Let us try to understand physically what is happening. We are assuming here that the diffusion is occurring by vacancy mechanism. And since more number of A atoms are moving from left to right than the number of B atoms from right to left, there is a net vacancy flow which is occurring from right to left, which we can denote as JV. Because of this, as the time progresses, there tend to be excess of vacancies on the left side of the alloy, whereas vacancies will be in short on the right side of the alloys. This excess and shortage I am talking with respect to their equilibrium concentrations, the equilibrium concentrations of vacancies. Now, in order to maintain the equilibrium concentration, on the left side the vacancies have to be annihilated, whereas on the right side of this couple the vacancies have to be created, and so the sources and sinks of vacancies will play an important role here. What are these sources and sinks? As we have seen earlier, dislocations and grain boundaries would act as sources and sinks. Since the diffusion couples usually are prepared with coarse grain size, the availability of grain boundaries is not much, but dislocations play a crucial role here. So, the vacancies will annihilate at dislocations. Similarly, wherever required, the vacancies can also be created from the dislocations. And how does this take place? So, if we consider an edge dislocation, and suppose there is a vacancy which comes closer to a dislocation line. Now, the vacancies may be somewhere there in the bulk. In order to get annihilated in the presence of excess of the vacancies will be transported to the dislocation, the nearest dislocation, and then when it comes to the near to the dislocation line, the vacancy will jump into the dislocation line and an atom will make a reverse jump. This way a vacancy will be introduced into the dislocation and the atom will be introduced from this extra half plane into the bulk of the crystal. This way, if more and more vacancies get annihilated at this dislocation, this entire dislocation line or this entire extra half plane will vanish. So, wherever there is a excess of vacancies, that is in this case on the left side of the alloy, the extra half planes will vanish, and so this side would look like it is shrinking. Whereas on the right hand side exactly opposite process will occur, because the vacancies will be created there. So the vacancies will be introduced into the lattice and extra half planes will be introduced, and hence this side will look like it has expanded. And this is how physically the marker will look like, as if they are moving in the direction opposite to the direction of diffusion of the faster moving components, in this case opposite to the diffusion direction of A. Now we know whenever a vacancy is created, there will be one lattice side added to the lattice, and whenever a vacancy is annihilated, there will be reduction of one lattice side. And so if when we are considering the intrinsic diffusion, there will be an imbalance of the fluxes of A and B, and so typically JA plus JB will not be equal to 0. In case of interdiffusion, we know sigma Ji tilde equal to 0. This is for constant molar volume. If the molar volume is not constant, then sigma Vi bar Ji with respect to volume fixed frame is equal to 0. But when molar volume is constant, again the volume fixed frame coincides with stationary frame, and the sigma Ji tilde is equal to 0. But this is not the case for intrinsic diffusion, and that is why dA and dB will be different. But if we consider the conservation of lattice side, then we also have to take into account the vacancy flow or the vacancy flux, in which case we can write sigma Ji plus Jv should be equal to 0, and so Jv is equal to minus summation of Ji. So for binary diffusion, this would be minus Ja minus Jb. So in order to get to the intrinsic diffusion coefficient, we need to track the original lattice plane, and this can be done only with the help of markers. How do we select these markers? Let us consider an analogy for this. So if we consider a small reservoir of water, and let us say initially the water was still, and if I introduce thin plane of ink at t equal to 0, we know the ink will start diffusing as the time progresses, and the diffusion profile would look something like this. These are the diffusion profiles at different times. So at any plane x, if we want to find the diffusion flux of ink, we just need to consider the intrinsic diffusivity of ink in water, because the diffusion is occurring only because of this concentration gradient and there is no drift present. Now in the second case, let us suppose now the water is flowing towards right. Of course the flow is not as fast, so that the diffusive flow and the drift are comparable. Then in that case, as the time progresses, this Gaussian type distribution will also shift with time, because the water is now flowing. Now if I want to evaluate the flux at the same position x, I now need to consider intrinsic diffusion as well as the velocity of water. What I can measure is the total flux, that is the interdiffusion flux, but in order to separate the intrinsic term from there, I need to measure the velocity of water. Let us call it V. How can we go about it? One easiest way is I put some wooden chips on the surface of water and I track the velocity of wooden chips, and I can approximately take the velocity of wooden chips as the velocity of water. Now, what is the criteria for wooden chip to act as a marker here? First, it should flow with water, then it should not react with water. That means it should not dissolve or it should not have any chemical reaction with water. Otherwise, we will lose the chips and we won't be able to track. In the same fashion, we need a marker which can stick to the lattice plane and which is stable at the diffusion temperature, which means the marker should not diffuse in the matrix and also it should not react with the matrix or with the other diffusing elements. And that can be done if we place these markers on the initial contact plane before we sandwich the two alloy blocks before the start of the diffusion experiments. Typically, the oxide particles like alumina or yttria are used for this purpose. Also, molybdenum is a very high melting element and the diffusivity of molybdenum at lower temperature is usually very low. So, molybdenum particles can also be used as markers. In fact, the first experiment reported by Smigelskas and Kirkendall, they used the molybdenum wire as the marker. So, I would like to describe that experiment briefly here. So, what they did, they took a rectangular bar of brass and they wrapped that bar with molybdenum wires, then they deposited about 0.1 inch thick layer of copper onto this block. So, if we take a cross section, it would look something like this. So, we could see the molybdenum wire cross sections at the initial contact plane. Then they diffusion annealed this assembly at a higher temperature isothermally for different times, and after various time intervals they observed the distance between these two markers, and what they found, as the diffusion time progressed, the distance between the two markers kept reducing. That means the markers moved from the initial interface into the brass side. Since copper was diffusing from outside into the brass and the zinc was diffusing from brass into the copper, obviously this would have occurred because of the faster diffusion of zinc from inside out compared to the diffusion of copper from outside in. And this was a classic experiment because it helped in establishing diffusion mechanism based on vacancies, which was not popular at that time. Earlier the popular mechanisms were the direct exchange mechanisms or ring mechanisms, but this helped giving a strong foundation for the vacancy mechanism of diffusion. In fact, because of this, Kirkendall also found it very hard to publish this work, but finally it got published, and then the vacancy mechanism also became very popular later on. Then Darkin later on analyzed the diffusion based upon this new frame of reference, which is now called as Kirkendall frame of reference, and he developed the interrelation between the interdiffusion fluxes and intrinsic fluxes. So, let us try to derive that equation, which is known as Darkin's equation. Now, we will work with constant molar volume case, and we will work with a binary system. We know based upon the conversion of fluxes from one frame of reference to the other, the intrinsic flux J1 with respect to the Kirkendall frame of reference can be expressed as J1 tilde minus C1 times Vk, where Vk is the velocity of the marker. Write the equation for 2, it would be J2 tilde minus C2 times Vk, and if we take the summation, which is basically J1 plus J2, that should be equal to summation of Ji tilde minus Vk times summation of Ci. Now Ci is the concentration in moles per centimeter cube. So the summation of Ci will be total number of moles per centimeter cube, which is equal to the inverse of molar volume. So we can write summation of Ji is equal to minus Vk over Vm, or the velocity of the Kirkendall frame of reference can be written as Vk is equal to minus Vm times sigma Ji. For binary, this would be minus Vm times J1 plus J2. So if we substitute back into the equation for J1, we get J1 is equal to J1 tilde plus C1 times Vm times J1 plus J2, but C1 times Vm is nothing but the mole fraction of 1 x1, and if we rearrange the terms, we get J1 tilde is equal to 1 minus x1 times J1 minus x1 times J2, and 1 minus x1 is nothing but x2. So the interdiffusion flux can be expressed in terms of intrinsic fluxes of the two components as x2 J1 minus x1 J2. Now if we substitute for fluxes in terms of Fick's law, we get minus d tilde dou C1 by dou x is equal to minus x2 times d1 dou C1 by dou x plus x1 d2 dou C2 by dou x. And for constant molar volume, we have dou C1 by dou x plus dou C2 by dou x equal to 0. So dou C2 by dou x is simply negative dou C1 by dou x. If we substitute here, we get minus dou tilde dou C1 by dou x equal to minus x2 d1 dou C1 by dou x minus x1 d2 dou C1 by dou x. Get rid of this gradient term, and we get the interrelation between interdiffusion coefficient d tilde and the intrinsic coefficients d1 and d2 as d tilde equal to x2 d1 plus x1 d2, and this is the famous Darken's equation. This helps in converting the interdiffusion coefficients into intrinsic or reverse. Now how do we actually determine these intrinsic diffusion coefficients? We will see in the next class. Thank you.